Good afternoon. Today I will present our work on developing a predictive model for a vacuum tube solar thermal system using long short-term memory neural networks. The goal is to improve temperature forecasting and enable more energy-efficient operation of real solar heating installations. Vacuum tube solar thermal systems are widely used for heating, but their efficiency depends strongly on accurately predicting temperature dynamics. These systems exhibit non-linear behavior, strong thermal inertia, and sharp transitions caused by sunlight and pump operation. Traditional analytical models often struggle with these effects. Machine learning, however, provides an opportunity for real-time, data-driven optimization. Our task is to predict the next temperature value for three key signals: the collector outlet, the collector inlet, and the hot water tank. The goal is to capture non-linear thermal behavior, including rapid transitions, and to enable intelligent control of the solar thermal system. We compare a modern deep learning model with a classical machine learning method. The objective is to develop and compare an LSTM neural network and a random forest model for temperature forecasting. By evaluating both, we aim to identify the approach that provides the most accurate and stable predictions, and thus contributes to improved energy-efficient operation of solar thermal systems. The solar thermal system examined in this study is part of a hybrid installation in a 3-story residential building in Plovdiv, Bulgaria. It comprises a pellet boiler, a 300-litre storage tank with 2 internal coils, multiple circulation loops, and a vacuum tube solar collector with 30 tubes and an effective area of about 2.5 square metres. Morning shading from a neighbouring building limits irradiation until approximately 10:20 a.m. Water circulation is ensured by pumps P1 and P2, with P2 controlled by a differential thermostat comparing the collector outlet temperature with that in the middle of the tank. The pump activates only when the collector temperature exceeds 40 degrees Celsius plus a user-defined differential, typically 4 to 20 degrees Celsius. During summer operation, the tank's electric heaters, 9 kilowatts total, remain as backup. Measurements were recorded continuously over a 10-day period at the end of August and beginning of September, capturing representative daily heating and cooling cycles. We collected experimental temperature data from 3 locations: the storage tank, the collector inlet, and the collector outlet. Over the 10-day measurement period, the system produced 13,622 temperature samples. These measurements capture strong daily fluctuations, from early morning cooling to rapid temperature increases once full sunlight reaches the collector. The dataset includes all characteristic behavior of the system: non-linear thermal responses, sharp temperature spikes when pump P2 activates, and gradual cooling during the night. These features make the dataset well suited for training predictive models based on artificial neural networks. The collected temperature curves were used as input vectors for model training, forming a reliable basis for forecasting the system's performance. Our long short-term memory neural network model uses a single layer with 64 units. The internal gating mechanism and cell state allow it to retain long-term temporal information and capture nonlinear dynamics and thermal inertia. A dropout rate of 0.2 improves generalization. The model outputs a single temperature prediction and is trained using the Adam optimizer and mean squared error loss. The random forest model consists of 300 regression trees with depth limited to 20. Because random forest has no temporal memory, we provide 180 lagged input features. Although robust for static dependencies, the model does not fully capture sequential dynamics, which limits its performance during sharp transitions or rapid temperature changes. Here we see that the long short-term memory neural network predictions follow the measured tank and outlet temperatures with high fidelity. The model accurately reconstructs daily heating-cooling cycles, rapid increases due to solar irradiance, and gradual nighttime cooling, demonstrating its ability to learn non-linear temporal dependencies. For the inlet temperature, long short-term memory neural network again aligns closely with the measured data. The training and validation loss curves converge smoothly, indicating stable learning and no overfitting. This confirms that the selected architecture is well suited for this type of thermal time series prediction. When comparing both models directly, the long short-term memory neural network clearly outperforms random forest. It follows rapid heating and cooling transitions more accurately, whereas random forest tends to lag behind or over-smooth the changes. Long short-term memory neural network maintains closer alignment across the entire cycle. The inlet temperature comparison leads to the same conclusion. Long short-term memory neural network remains closer to the measured curve during both smooth and abrupt transitions. The evaluation metrics confirm this. The long short-term memory neural network model achieves consistently lower root mean squared error and higher R-squared across all three signals, demonstrating superior accuracy and generalization. In conclusion, the long short-term memory neural network model consistently outperforms random forest. It captures nonlinear and time-dependent thermal behavior, provides more accurate and stable forecasts, and supports the development of intelligent, energy-efficient control strategies. These results indicate strong potential for real-time deployment in solar thermal monitoring and optimization. Thank you very much for your attention. I will be happy to answer any questions.